Good morning and welcome to Race Industry Now, the weekly webinar series from EPARTRADE, presented to you by ARP, Performance Plus Global Logistics, Feria Racing Components, PIC, Fifth Third Bank Motorsport, Quarer, and CTEC Manufacturing. I am Francisco Savignan, the founder and CEO of EPARTRADE, the racing industry, every minute, every day. This is episode 536, and we're going to be talking with Bruker. With me this morning are Judy Kinn, the co-founder of EPARTRADE, and our superstar host, Mr. Jeff Hammond, three-time NASCAR crew chief champion. Judy?
I love when you do that to Jeff here, but thank you everyone for joining us today. Today is just the prime example of all the cool technology, high-end products that we have showcased on this racing platform. So if you have yet to sign in, please do. It's complimentary. It's really like walking the aisles of trade shows. You don't know what cool machines are out there, engine parts, and that's why we created this racing destination. So it's an all-year platform. Jeff?
Well, thank you both. It's great to be here today. And the thing is, folks, in doing a little research about our guest and what we're going to be learning, you're going to be learning right along with me. I mean, there's a lot to learn about what we always talk about, coatings and drag and how you can make a product better. Well, this is a different angle, I think, that we're going to see today. And I'm really excited about it and what Mr. Robert Wang is going to be bringing to us here in a moment. So make sure you got your questions ready. And at the same time, we got a lot to learn in a short period of time to get it done in. So let's get the show on the road. There he is, Robert right there. Good morning, sir.
Good morning. Hi, Jeff. Nice to meet you all. Good to see you.
Good to see you.
Good to see you. Yep.
Well, thanks for having me. Yeah, I appreciate it. Sorry.
Yeah, I think right now, that can you explain a little bit about your company that you work for, and kind of like give us a foundation, a little cliff deal on it, please.
Yeah, absolutely. So, yeah, hi everyone. I work for Bruker Corporation. Bruker is actually a very big company that handles a lot of different testing equipment across different industries. I personally manage a few different products of that company, and the products that I manage are sometimes directly related to the automotive industry. So the things that I manage are the TriboLab tribometers, which test for friction and wear. I also manage our optical profilometers and our stylus profilometers that are used to measure the surface of a material. So between all of these different systems, you can sort of get a better idea of the performance of, let's say, a gearing shaft or a steering rod. You can look at the properties of brakes and sort of analyze what you're doing on the back end with your manufacturing, and then how that affects the front end performance of your vehicle. So all of that sort of allows us to provide a bit of synergy and a bit of understanding to how and why your materials perform the way that they do.
So what you're telling me there, so what would be the potential of these systems helping make modern advancements in the automotive industry? I mean, this is an area that I don't think a lot of us are exposed to on a regular basis.
Yeah. So I should probably start by saying I also am very passionate in racing. I actually do a few different karting leagues, and I don't have as much money as, as some to do sort of full-on automotive racing, but I'm very passionate about it. So what I've noticed is in a lot of different areas, people focus a lot on measuring the performance of a car when it's running, which is super important, of course. But of course, a lot of the time, that whole R&D development process begins in the lab, right? It begins at the factory level when you're bringing materials together. So when it comes to that, a lot of the time you actually need to be able to understand, for example, what kinds of compounds are going to affect performance in different ways. And one of the main things that are missed out is, for example, number one, friction and wear testing at the material level, and number two, surface metrology or profilometry, some might call it, regarding, for example, what the roughness is of certain surfaces. These kinds of parameters really impact, for example, the frictional wear on your tires. It can impact, how your brake handles over time. It can impact, for example, what engine oil you end up using for specific types of races, and it affects, for example, the compounds that you end up using as well. By changing the chemistry of certain oils, that might change the lubricity, that might change the performance under certain conditions. And we basically try and help provide a little bit of knowledge and expertise, before any of that has even gone into the car as to how that's going to perform.
Okay, so understanding what we're saying here for me is that, we spend a lot of time looking at, coast down, for example, on a
Mhm.
chassis dyno. We know
Mhm.
what you do to get up to make the power, but how much power is being robbed from different components. So what you're saying is you're going to allow us to help make that better, no matter what we're looking at, whether it's tires, brakes, gearboxes, oil, everything like that goes into something that racers more than likely would be more interested in, because drag coefficients and everything that those kind of surfaces. Do you have the ability to look at a surface and think and talk about how you can reduce drag as far as even aero is concerned?
That's a great question. Let me give you an example. Let's think when you spray coat a surface of a car, right?
Mm-hmm.
That is the predominant surface area that's exposed to air as the car drives through. What we've noticed is when you measure the surface profile of the car very closely, if you get a small 3D profile of that surface, depending on how your surface looks at a very small level, that can impact how the air moves over it, right? Whether the airflow is turbulent, whether it's laminar, and whether or not that will impact the end lap time. So by understanding that surface, the surface of your material at a sort of almost molecular level, a lot closer, you can understand how the end performance is going to be. And you have a lot of different, surface parameters that we use on our side, not just in automotive, but it's definitely applicable, where you can, analyze, for example, if I was to change this specific property, or if I was to polish it in this certain way, does that end up affecting, for example, the drag that I get? And that's just one example of where that would be used. Absolutely.
And see, now I find that fascinating because my old school days of going to a wind tunnel, and we put the tufts on there, which were basically,
Mhm.
pieces of yarn. And the way that tuft handled, if it laid down flat and didn't move, then it's telling you one thing. But at the same time, if it's being influenced by, a curve, and however the surface condition is, it may make it do like a flag that's flapping around in the wind, and it would start to come apart. So you could get, derive some kind of what do you think? What do we need to do here?
Yeah,
So you're able to try to help us understand with surfaces just as well as we were trying to understand what we didn't understand. Yeah.
absolutely. Absolutely. And, that's a great example, because with the wind tunnel effect, I mean, it's great. You need to test stuff in person, right? That's never going to be taken away. No one's ever going to stop testing, for example, a car when it's running, right?
Right.
But the disadvantage of doing that all the time is that it does take a lot of time and money, right? You have to, try different combinations, then run it again, see if that's made a difference. What the profilometer or the tribometer would do is it would help you run through those potential possibilities a bit quicker. It allows you to do it on a sort of almost like a lab level, where you can do it on a benchtop system, test it out
Mm-hmm.
beforehand without having to get the whole thing into a wind tunnel, run it for hours, then run it back and get all that data. You get the data front hand, and that allows you to save a lot of time and money to predict better what combinations are actually going to work for you. So you'll still run it in a wind tunnel, but at the end of the day, the number of times you have to run it there to get to the result that you want should be less. And that's where these kinds of systems really do very well.
Well, speaking of those kind of systems, I believe you have a PowerPoint presentation that might allow us to understand this even better. And
Yeah,
folks, those of you who are out there today, listening and everything, remember, we do accept questions. So please feel free to do this. But what we're going to try to do, if you got a question, fire it on in. But at the conclusion of this PowerPoint, we'll open it up, and we'll go back and answer any questions that have come up before we even start. But at the same time, we'll definitely answer them before we get off the air today.
perfect. Yeah, absolutely. So why don't I go ahead and let me share this screen here.
All right.
Hopefully everyone can see that okay. Starting a bit
Yes,
later on. There we
I'm
go.
seeing it good. Very clear.
Awesome. Fantastic. Yeah. As Jeff mentioned, if anyone has any questions, please feel free to let me know. Hopefully I can see if someone raises a hand, but again, Jeff, everyone, please feel free to stop me if there are any questions as well and I miss it.
Okay.
Great. So why don't I introduce essentially what we do a little bit? I know I spoke about it already. Essentially, the Bruker tribometer has been around for quite some time. It actually used to belong to a company called CETR, the Center for Tribology, and that was bought out by Bruker back in 2011. So for about over 15 years now, or just coming up to 15 years, we've been able to sort of perfect the system a little bit more. What essentially the system is it is a modular friction and wear tester, right? Quite often in tribology, what you end up getting is you have one big system that tests one particular motion. So, let's say, for example, you're rotating one brake pad and applying a force from the top. That would be one type of test, right? What the TriboLab does is something similar to that, but also slightly unique. It allows you to change the conditions of your motion, of your conditions, of your forces in one usable system. So rather than just being restricted to rotary motion, for example, now you can do reciprocating back and forth. You can do linear motion in a line for scratch testing, for example. You can do, for example, block on ring, right, where you're testing it with a horizontal axis of rotation. So there's a lot of different things now that we have applied to one system. And that in particular, that flexibility is something that we see very useful in the automotive industry, because fundamentally there are a lot of different moving parts in a car, right? You can have a lot of different kinds of motion, whether it be, your steering axis and that sort of motion with the steering rod, having to brake against another surface. That's a different kind of motion to when you have two brake pads going at it against each other, right? And the ability to be able to test all those different things in one system is what a lot of our clients end up using this system for. So bear that in mind when I go on to the next slides as well. You can see this is sort of the original tribometer from CETR. This is back in 1993, so quite old. I don't even believe it was using Windows. I mean, I can't remember what version of Windows that was, but it was manufactured in California, and I'll show you in a second what it's become today. So in essence, a few of the different standard kinds of tests that we run on these kinds of systems are, as you can see here, these are a few different ASTM standards, right? You've got a standard configuration of ball or pin on disc, where you apply a pin and you're rotating a surface beneath it. You've got ball or pin on plate, where you've got a pin coming down and it goes back and forth, right? You've got 4-ball testing, where you have a ball coming down again and you've got 3 balls rotating around it. All of these, again, mimic different kinds of motions. And we study all of that, basically, with the system. And the way we can do that is with a combination of different modules. I'll also go into a little bit of detail about the kinds of environments that we can replicate. Because, of course, in a car, for example, as you drive more and more laps, your car heats up, right? You want to test those conditions at different environments as well. You can test, for example, in a humid environment, if you're driving in Texas, for example, in summer, versus if you're driving, let's say, in Canada in the winter, you can test all of those different conditions too. And we'll go into that in a bit more detail as well. So again, really what makes the TriboLab itself unique is the ability for it to basically take on and off different drives. And I'll go into how the TriboLab looks here as well. But one of the most important components of this is on the bottom chassis, you've got essentially the ability to screw on and off various different drives. And this is what controls your sample movement, essentially. You can see here, this is a rotary drive that's on the stage at the moment. And what the TriboLab does is it has what's called a TriboLab ID, where it essentially reads a barcode underneath the drive, and it automatically reconfigures all of the testing parameters for that specific motion. So if you've got, let's say, a rotary motion, the system will tell you how many RPM do you want it to spin at for how long? Do you want it to reduce the RPM after a certain amount of time? Do you want it to reduce at a certain rate? All of these things can be really easily controlled, which is what makes it very, very applicable in real world conditions, right? You're not restricted to having to run it in a certain mode for forever. You can have it be adaptable. And you can see some of the other drives here as well. This is our block on ring drive here. where it sort of rotates like this, and you're testing the wear. You also have a reciprocating drive, which goes back and forth, and then a linear drive as well. I mentioned environments. So when it comes to looking at the actual environments that you have, there are a few different things that we can replicate. And one of them is, for example, liquid testing. We can actually submerge this in a liquid and have your samples tested as well. So, with this, you can think lubricants, right? If you've got a surface submerged in, let's say, an oil, you might want to test the friction and wear as you change the compounds of that oil. And that is something that we can easily do. Another type of testing is high temperature and low temperature testing. So we go down to minus 40 degrees C, and we can go up to 1200 C. So there's a big sort of temperature range that you can control. And again, being able to test the changes of your brake conditions, or being able to test the different frictional properties of your polymers, for example, at these different temperatures is often very, very useful as well. And then finally, we do have a humidity chamber as well here, which again allows you to control the humidity that you're in, which can often, for example, affect corrosion properties too. In terms of the system itself, you can see here what it actually looks like. This is a benchtop system at the end of the day, but it does test, pretty much real world conditions within it. And you have, you can see here, this is where your lower drive would sit, but up here, and by the way, can everyone see my cursor? Hopefully you can see that. Okay.
I see it.
Awesome. You can see this is the upper sensor as well. So this sensor is what essentially gives us all of our force capabilities. It both simultaneously applies and receives a force, right? So you tell it, I want to apply 10 newtons at this amount of time, and it will apply it, but it'll also read back to itself how much force is being fed back by the sample and how much force is being received. And by doing that, you can literally track the frictional coefficients of friction and the frictional forces during the test itself. So for example, if you get any slippage, let's say you're testing two brakes, right, and it slips momentarily, that will have a frictional change and it will be read by the system. So all of these parameters can be analyzed quite significantly. And again, when it comes to racing, that can mean the difference between understeering and oversteering, right? So that's really where the system would be useful in this case. And here are a few of the different systems that we have on our product line. You can see here, this is our standard TriboLab itself. That's the most versatile benchtop unit. We do have a dedicated brake friction tester as well. That is called the TriboLab HD, or heavy duty. And essentially that is a standalone system with a much higher torque that can allow you to really get brake testing done efficiently at a lab scale. And that system would be really just used for brakes mostly, and particle emission studies. And then finally, we do have what's called a CMP as well. This is our polishing tool. Most of the time, this is used more in wafer analysis, so not really in the automotive, but it can also be used for some unique polishing applications across different industries as well. So I thought I'd just add that in there just to let everyone know. But essentially, between these systems, you'd be able to test most tribological components within a car. So like I mentioned, the TriboLab ID is what sort of lends itself to the flexibility that the system has. You don't have to change any of the system to allow it to be, I guess, configurable. But what makes it unique is the ability for it to essentially be installable by any engineer at any time to do different kinds of tests. And you can see here, these are a few different specifications of the lower drives that you can see the types of testing that you can do as well. So I'm going to go ahead and show you a quick image of essentially the different kinds of tests that we do and the different kinds of properties that we would then measure. And then I'll speak a little bit, hopefully we have some time, about the optical products that we have as well, because we do have some profilometers that go hand in hand with this to help you look at, once you've made the wear scar, what does that look like at that point? So, here is just an example again of the different kinds of tests in action. You can see the different environments that we have. And a lot of this would be applicable again in the automotive industry. This is getting a little bit technical now. I thought I'd add this slide just to show people what the actual output of a TriboLab looks like, right? You apply a force, but what does the system give back to you? And this is one example of what it can do. This was a test done at high temperature, and we essentially did a drift test here, a thermal drift test, where you could see the force changes as a function of time as you started applying, a known force by the upper sensor. And you can see that over time, as a function of this high temperature, your force as a function of the normal force, the Fz, increased significantly, whereas your Fx, the frictional force going in the lateral direction, decreased. And so that allows us to measure, for example, force drift as a function of the time that it was measured at as well. And again, these are just standard tests that we do with the system. Okay, I'm going to take a quick pause there. I don't know if anyone has any questions. I'm happy to field them. If not, I'm also happy to show some of the profilometry side of what we do as well. That would be allowing you to see the surface of your material very closely. Were there any questions, or did anyone want to ask anything at this moment?
I'm curious about, when you're, for example, with brakes,
Mm-hmm.
Do you take, what kind of sample size do you have to be able to accomplish something, and get a understanding of whether or not it's working or not?
Mm-hmm.
And is it a combination, because you got a brake pad, it's one type of surface, and then you got the rotor, which is another type of surface. So to find out what the two of them are doing as far as matching up, do you have the capability to be able to repeat that, or do you, what is it? How much of a sample size do you have to have?
Absolutely, that's a great question. So our system accommodates up to 4 inches of sample size, and fundamentally, the sample size does not have to be as large as what it is in person, right? You can have it tested for the direct sample that's being used in a car, but oftentimes when you look at friction and you look at the properties that those materials have, you can already test that at a much smaller scale. So let's say, for example, you have, I don't know, a lubricant that's essentially helping 2 pieces of metal rub against each other, right? Oftentimes, a lot of our clients will actually use maybe a 1 centimeter coupon of that material, have another 1 centimeter coupon on top, and just rub them together with the same lubricant that's being applied. And that motion alone in that small area size will already give you a lot of information about how it will behave on a larger scale. Most of the time, you just want to make sure it mimics the bulk material properties that you would have. But again, this is not to substitute any of the actual back-end testing that you would do, right? You still want to run your specs and make sure you know what you're doing when the car is running. But this gives you much quicker access to information about how that material might behave before you've even had to go on the track. And so that cuts a lot of, I guess, it creates a lot of shortcuts to allow you to get to a conclusion better. For example, you might say, with a specific lubricant compound, I need to add, X% more of this compound or that material or that element. And that's going to help me to get better lubricant performance, let's say at minus 10 degrees C. So all of that would be useful there.
Okay, let me continue on that same line of questioning. You might say, you tested the brake pad and the rotor in your product, in your machine. Could you come back with that product that has already been run and do a post evaluation of where everything went to see if it replicates the simulation, how close it is as far as this is what the pad part did and this is what the rotor part did?
Yeah, absolutely. So one of the big things that we end up doing is, you run a material for a certain amount of time, you take it away, you allow it to perform in the condition that it's in, and then you can retake that same material and test the frictional properties again and have the data side by side to see how, for example, that friction has changed, how that coefficient of friction has changed. One of the big systems that we actually will end up using for that as well is our optical profilometer, where we can see the before and after shots of how your sample looks at a very high level. And the change in your sample surface will also allow you to predict how the friction has changed. So, the 2 steps to this is looking at your surface, predicting from your surface what the frictional and performance properties will be of that surface. Then running it on the TriboLab as well. Once you've done that, you understand essentially, what about my manufacturing process has created this property and how does that property actually look? And then once it's actually gone ahead and performed, you take it back. You can then, again, analyze the same surface. You can see the changes that surface has undergone physically. And you can also then remeasure the frictional properties of that. And that gives you basically a comprehensive view of, number one, why your sample performed well or not well. And number two, what happened during the race, for example, where something has changed, and you can analyze that again on the back end and compare it to where it was at the beginning.
Very good.
Absolutely. So I'm just going to cover interferometry real quick as well. It's a big word, but essentially it is the technique that we use for 3D profilometry. Looking at a system, you can almost think of it as if you take like a 3D scan of something, you're looking at that surface, then imagine you taking that scan at an atomic level, right? You're looking really closely at something. We're essentially doing that, right? We're looking at this material down to the atomic level, and we're looking at all the small hills and bumps that you might see at that level as well. And the benefit of this is essentially you're looking at a high resolution, so you're able to see these small, features that will actually impact the end performance. Oftentimes with 3D scanning, when we 3D scan a car, for example, most of the time it's looking at that large level picture, right? Which is also very important. But that stuff is not going to impact, for example, the friction that you experience with drag when you're moving a car at 180 miles an hour through the air, right? That is not just influenced by the geometry of your car, but also of the surface finish of your car. And so all of that will play a bit of an impact as well. So that high resolution imaging is really what Bruker does really, really well. And more than that, we do it on pretty much any kind of surface, right? We do it on curved and shiny surfaces. We can do it through transparent surfaces, whether it be glass, or an acrylic. We can do it on non-reflective surfaces, so stuff that's been painted in black, for example. There isn't really any restriction to the type of surface that we measure. But fundamentally, what you're going to get is profiles, 3D profiles like this, which allow you to see, what you can't see by eye, which is how does my surface actually look? And more importantly, what are the numbers that I can use to then better control my manufacturing and then my back-end processing as well. Numbers is the big key in this, and I'll go to this in a bit more detail here. The big difference between an interferometer and a standard optical profiler is that you're looking at high resolution across any area size that you want to measure, right? Standard optical profilometry is more centered around getting a nice picture, taking a 3D profile that's roughly correct, and then moving on. The interferometer focuses much more on getting accurate data and numbers. So I don't know if anyone's familiar with surface finish, but SA here is the surface roughness. And the roughness is really just essentially, if I was to draw a line through my whole surface, which best fits it, how much does my surface deviate, right? Is it very bumpy? Is it not bumpy at all? And that is essentially the definition of roughness. And it's governed by an equation. Now, that number we often see impacts the performance of a lot of different things, right? It can impact the visual appeal of a paint. It can impact how your car is going to move through the air. It can impact, how your brakes are going to behave relative to each other. That roughness governs a lot. But there are a lot of other parameters out there that allow you to characterize your surface and predict how your system's going to behave. So again, when we look at this, we are taking a nice 3D image that you can see like this. You can see this is a crosshatch on a fuel engine that you can see pretty clearly with this system. But more importantly, it's giving you back cold hard data that you can also use as part of your back-end process. So if, for example, you wanted to try out a new polishing technique, right, for a certain part, you can do that and run both the old polishing sample and the new polishing sample on the system and analyze all of the different ways, all of the different properties at the surface level to say, well, okay, this one had a smaller roughness than that, but maybe this feature was sharper than that one, and that was what impacted my end performance at the end of the day. You can get really technical about, how does my system behave at the surface level? And so that's why we called this presentation today, Understanding Things at the Surface Level, is because your surface of your material will oftentimes determine, when a car performs well and when it fails. And the ability to do this repeatably is what a lot of people end up using it for. I know a lot of people in the chat might be quite technical, so I thought I'd just quickly go through this as well as to how this system works, and then I'll field any questions because this might invite some. Essentially, what this system is doing is it's shining a beam of light into what we call a beam splitter. And some of the light is going straight down towards your sample, and some of it's going perpendicular. That's what the beam splitter will do. And the light that's being reflected back from your sample will go into the detector, as will the light that shines from this, what we call a reference mirror, which is very smooth and flat. And when both of your light comes back into the detector, it creates what's called this interference pattern. Essentially what it is this is a pattern that is caused by the constructive and destructive interference of your light across different areas. And this is what we use to essentially probe the surface. So by using this pattern, we can look at a surface very, very closely, and we're actually very sensitive even to the atomic level. So if you have a super polished surface that has maybe a nanometer of roughness, for example, you're still able to measure that very accurately and be able to determine, is this 1 nanometer, is this 2 nanometers, is it 0.5? That is not a problem for this system either. And so you can see there are a few different scanning modes that we have. The vertical scanning mode is by far the most common. It allows you to, get images like this where you scan through a large range. You've got a decent resolution. It's not the best in class that we'll show in a second, but it's very good. And it gives you the ability to measure larger features very accurately. You can see that here. You can see the fringe that scans through as your lens moves down. And that helps you characterize essentially the surface of your material. And you'll see that here in just a second. There we go. So once it scans through, it will produce a pattern like this, and that is essentially your surface. We do also do some ultra high resolution scanning with the phase of the light as well, and that's called phase shifting mode. And this is where we essentially just look at the atomic level changes of your surface, and that small atomic bump, for example, that you may have will cause, a slight change in the phase of the light, the path difference of the light, and that gives you a very high-end resolution. So this essentially is a glass mirror that was hyper polished to 0.09, I should say, nanometers, or just about 1 angstrom. And that gives you essentially the ability to see things at a very, very high accuracy level. So, if you've got like a super smooth part in your car, this is the mode that you would use. And fundamentally, we also have a combination of the two as well. It's Bruker's unique mode called universal scanning interferometry. This gives you that ultra high resolution and ability to scan through a long surface and do that accurately. And this is using essentially an AI algorithm to combine both methods, essentially. So between that, you have a lot of different ways of being able to essentially combine analyses and get very high resolution data. And just to take a step back, if we were to relate this to the automotive industry, this would be the system which you use to look at the wear scars on a brake pad, for example, or this is the system that you use to look at the paint on a car, right? You look at it at the beginning, you can look at it at the end, you'll see the differences in the surface texture. You can even subtract one profile from another and see, for example, how much your brakes have worn down over a certain amount of time, or you can see, for example, how much of a wear scar was produced on a certain part of the system as well. So you can essentially use this to measure any kind of surface that you have. And sort of by illustration, in this case, you can see these exact examples. This is what the system looks like in general. This is our benchtop optical profilometer. We also have larger systems as well that test larger samples. But you can see these are the different kinds of wear that you might end up seeing on your car, right? This is most likely a worn down ball bearing. You have other forms of texture as well. This is a great example of corrosion down here. where, you may have been in a certain environment and your metal has corroded, right? So again, it allows you to look at all different aspects of what your car and material may have undergone throughout the testing and throughout the driving as well. And then finally, this is a thrust washer test that some people might be familiar with, where we essentially looked at the upper stationary sample, and you can see that there was some galling that occurred. You can see the locations of the test as well. And essentially there was some abrasion that went on, and we were able to test the abrasive wear pattern and even the volumetric loss of the material at a certain point. And all of this, again, relates back to the friction and the performance of your car, right? Like if you think about a hard and a soft tire wearing down over time, the reason why you get less grip, right, as you go throughout the race is because the tire is losing traction with the ground. And the reason it's losing traction with the ground is because the surface of the tire is changing, because all of that friction is causing the rubber to wear off, and your tire is actually getting smoother, which basically means that the amount of contact points that your tire has with the ground is reducing. And that fundamentally is why you're losing grip, right? So when you consider that, you can understand then better how looking at the surface of that material would help you better understand, can I get tires with better grip over time? Can I start with a tire that's better, even before I've started the race? What is the theoretical best grip for a tire? And, how does my compound changes also affect that as well? All of these different things are impacted and can be analyzed by these systems. And again, apologies, I'm throwing a lot of different scenarios at you, but it's only because there's a lot of different things that this kind of system would be able to help test. And hopefully it just gives some people some ideas about, what they might end up using this for. So with that being said, I thought, I didn't want to take too long over this. If anyone has any questions, again, please let me know. Hopefully that helps here, and I'm happy to stop sharing my screen here as well. Unless anyone has any questions.
Yeah, like I said, folks, you got something, please send it over so we get an opportunity to share it with Robert. But even for me to sit here and listen to what your capabilities are, my head's just spinning thinking about it's like you got an idea, but it's like the idea of being able to fail and come back and repeat what you fail, and without having to keep going back to a track, or you can do sampling, or what I'm saying. It looks to me like you can do a lot more targeting more concisely in a shorter period of time to come up with a conclusion that this is the direction we need to go in versus not, because
Exactly.
I know that the ability when you're loading a product, a lot of times during testing, the inconsistency sometimes of the load or the angle of the load, it really challenges you. And I see right now that y'all have tried to eliminate a lot of that and give more options than it's not just a single dimensional deal or even a multi-dimensional. It's multi-dimensional.
Yeah, exactly. And that's where this world becomes so fascinating and so complicated, right? Is when you design a car, or as a racer, even when you drive a car, you're thinking about all these different things, right? You're thinking about the temperature, you're thinking about the track, you're thinking about what parts of the track have rubber on them already, what parts of the track are warm, how is my engine going to perform over time? All of these different parameters. When my car gets lighter, how does that affect everything? So what this system does is it cuts through a lot of that thinking on the track. It brings it back to the lab. It allows you to predict it before you even had to. And at the end of the day, it's the racer's instinct that's going to take over at that point, right? Once it gets on the track. So this just basically helps the R&D team design better product to where they can provide something that is more synonymous to what the driver wants, right? If the driver says, I'm losing traction in turn 13 because it's a super, heavy right turn, for example, I don't know why it is, there are only a few different types of motions that might be going on at that time that you might want to predict, right? Like if you're taking a tight right turn at a low speed, that's a different kind of motion on the tires and on the engine than it would be for, a fast turn on a left turn, right? And this system basically allows you to summarize maybe why, certain turns might be more difficult in that example, and boil it down to a number or a set of numbers that maybe your material isn't where it should be for that specific thing. Again, it's not something you'll always be able to change on track or even at a race, but it is something which for an R&D team is particularly useful when they're actually designing the material in the car in the first place, right? When they're making the car, when they're trying to figure out what we're going to use for the majority of the year, that is where this system would be very heavily used and allow you to basically make a much better car.
Let me ask you this, you talk about your racing. Have you been able to take anything to the track and bring it back and just to, have fun running it through the machine itself to see if it's applicable?
Yeah, I'm really happy you asked that. So yes, here's the answer. If you go onto my LinkedIn, we actually have several publications of materials of the month, I like to call it. It's just stuff that I did for fun. I actually did one publication where we saw a worn down tire versus a new tire, right? And one that was, had a few laps in it versus one that was completely, track fresh. And, we were able to analyze that in a lot more detail. And you can literally see the changes in roughness. You can see the changes in surface texture at that level. And it's fascinating to see just, by eye what that looks like. But more importantly, I think for most people, you can see, for example, the different changes in the surface parameters. It's not just roughness, right? Roughness is one parameter. You have so many others that you can use. For example, there's a parameter called kurtosis, which tells you, on average, how sharp are my features? Not just how much do they go up and down, but are they sharp? Are they bowy? Are they, smoothish? All of that actually impacts performance too, if you think about it. So, we actually ended up testing all of that, and we could see clearly that there are some parameters that could predict when the tire wear was more compared to less, and when the traction might be reduced. So yeah, I'm always fascinated by stuff like this. In fact, I think the last materials of the month that we did, I tested like a biker helmet with like that kind of rubbery texture on the outside versus like an actual F1 or karting style helmet, which is very smooth. And we looked at those materials as well, and you can see the drag reduction that's caused by a smoother material versus a rougher material. So yeah, we love to experiment with stuff like this, but definitely it's seen some application already.
Well, the other thing that was kind of like fascinating to me was the fact you're talking about the surfaces, a polished surface, how rough this surface is, da 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 da. But that da 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 da, if you had both surfaces, exactly the same, is that really necessarily the best? I mean, something somewhere probably needs to absorb and dissipate heat, and the way that does that is by wearing. And so, if the two identical surfaces were the same, would it maybe, where would it transfer the heat? Where would it start doing? What part of the equation is a little give there to make it be where performs at its best and not create maybe too much surface contact, too much heat, and put it back through the instead of making it go maybe into the, for example, it's a bearing or whatever coating or surface, and you transfer it back into the hub. Does it possibly run the risk of overheating the outside bearing or something? I'm saying,
Right,
what
exactly.
What is the conduit of the two parts that you're putting together? Have the
Exactly.
same identical surfaces.
And what you just mentioned is a direct consequence of that, right? Like if your engine overheats, it's most likely because, I mean, let's say you put the wrong oil in, right? That specific oil may not lubricate properly under certain conditions. And the reason why your engine's overheating is because your friction is literally generating that heat. The heat's not coming from nowhere. It's coming from the friction on the engine. So yeah, exactly. You can analyze even the frictional, not just the friction, but also the heat that's being transferred as a function of that friction. But what I think is really interesting. Sorry. Yeah.
Real quick, we getting closer on time.
Sure.
Brian Neeb has asked us, based off our little dialogue here, would it build any heat? And
Yep.
there again, I don't know, but usually when you put two surfaces together, one of them is going to make the other one build heat. I mean, I'm assuming my logic tells me one of them would make it, would build some heat. One's got to absorb heat, so how would that play out overall?
Right.
Because again, sometimes you put surfaces together and you run oil
Yep.
through there. Well, one of them needs to have it to where it can bond the oil so the other one has the ability to ride on the oil. So it's like,
Exactly.
okay, and there's a fine line there. So that's what I'm saying here is you got a machine that can tell you where that fine line is and
Yep.
give you that direction. Now you got to go out and prove it.
Exactly.
And then, that to me is what this is all about, is that it cuts a corner instead of hopefully not tearing something up, but will
Yep.
tell you if you do it this way, the end result will be positive and not negative.
Exactly. And it just cuts down, again, it's all about being able to test different hypotheses quickly, right? When you're on a track and you have all these different conditions going on, you want to be able to run that without having to run 1,000 laps under different conditions. That's really where the testing becomes useful. And what I find is, so I'm a materials engineer by trade. That's my background. And, I studied, why materials behave the way they do from a physical and a chemical standpoint. And, I've spoken to a lot of engineers, and they're really great, generally speaking, at understanding, what changes to make to a car to help it drive better, right? Just as a general principle. But I think what a lot of people haven't talked a lot about actually is, how do I change things at the material level and the R&D level to make that less of a challenge in the first place when I actually go and design the car, right? And it's all about trying to maximize the parameters that you want in your car. Exactly as you said, for example, if you want to make sure that the engine doesn't overheat for a certain amount of time, that's all linked to how much friction you see and also the specific thermal capacity as well, like how well your material stores heat in a specific place. That all impacts, for example, when it builds heat, right? If you have a metal that, the heat distributes throughout the whole metal, that's going to hold less heat in a specific place than if you have like a rubber that's rubbing against each other and it doesn't dissipate heat at all. And you've got these really hot contact points that then are actually quite cold elsewhere. So being able to understand that end of the process, I think, is where a lot of people don't actually have a lot of information on. It's something that we've spoken to some clients on, but to be quite honest, I think there's a huge opportunity for anyone who gets into this area to learn a lot about it, because I don't think it's been fully studied yet, and it's got a lot of information that I'm sure would be helpful for a lot of people to get a better idea of what's going on with their machine.
Well, Robert, one other thing too, I do not want to overlook, and I see Judy's coming back. So ES said, "Hey, brilliant presentation, thank you." And
I
I thought it
appreciate that.
was well done. And I know we crammed a lot of stuff into everybody's head right now, but at the same time, I think that it's the right kind of cramming, because I think it's going to make them come back to you and try to say, "Hey, this here, I was thinking about it. Can you explain this?" And that's what we're looking for here, is trying to make sure that everybody understands that there's folks like you out there and your company that are asking these questions and getting the answers the right way, instead of having to say, well, we got to do trial and error, we got to do this, and we got to sit up for a month study, blah, blah, blah. No, we can go in here, we can knock it out, give you a direction and get on down the program. And being that you're a racer, you understand the need to be able to do that.
Absolutely. Yeah. And like I said, I'm all about trying to reduce that times. That's my goal. I love taking this stuff out on the track and then testing it. And I've never had the privilege to be able to do it, like I said, on a real life car, but I've definitely experienced it in my small racing career as well. And I think this will all result at the end of the day in better lap times and better positions, right? That's what it's about, I guess, as a racing team at the end of the day, is performance.
Yeah.
It's about maximizing what your material does so that you get the results you want and hopefully win. So yeah, definitely that's my priority as well. And I feel that.
Excellent. Thank you, Robert. What a great presentation. Thank you, Jeff. Great session today. And this webinar has been recorded. It will be posted later on the EPARTRADE platform, distributed through our newsletter channel and social media channel as well. Don't forget to check out Bruker's product. We push them back on the homepage of EPARTRADE. Next webinar will be on brakes with Delta ABS. For more information and updates, please visit epartrade.com. Thank you once again, and goodbye.
Thank you very much.
EPARTRADE is a digital platform that we've created basically to make life easier in the business community of auto racing.
EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier.
When you see a product that you're interested in, all you need to do is click on request more information, and then from there it is forwarded directly to the buyer or to the supplier.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Land speed record holder George Poteet's Speed Demon rocketed 481 miles per hour at the Bonneville Salt Flats. You don't go that fast without ARP fasteners.
There is no way that we could go the speed that we've gone, the number of times we've gone, with a lesser quality bolt than ARP supplies to us. And we absolutely wouldn't be where we were today if it weren't for ARP.
When failure is not an option, it's ARP-bolts.com.
We're Performance Plus Global Logistics. Our team of dedicated performance industry and logistics experts get valuable cars and components to the track on time in top condition. We provide expedited logistics solutions for the performance industry using direct routes instead of deferred options, and communicate all necessary information to the appropriate resources to meet regulations and ensure a smooth transit and secure delivery, both domestically and internationally. And we exceed customer expectations by providing best-in-class service with an efficient and cost-effective system in place. Contact us today to book your next shipment.
You work as hard as your truck, and you have no time for downtime. That's why more truck owners trust Blue Def, America's #1 diesel exhaust fluid brand. Each batch is guaranteed pure, so you can avoid costly repairs caused by inferior DEF. Demand America's best for your truck. Blue Def and Blue Def Platinum. Put trust in your truck.
With roots in the Midwest that date back well before the Model T, Fifth Third Bank has a long history of serving the needs of automotive companies. While much has changed over the years, our passion for helping businesses put cars on the road and on the track has not. Today, we are more committed than ever as a member of SEMA, a founding member of PRI, and a sponsor of multiple race teams across several racing series. Where can we take your business? Fifth Third Bank.
Where will you find Ferrea racing components, circle track, drag racing, and any top race shop? In every form of motorsports competition, our valves and valve train components deliver race-proven design and technology. And we've brought that same performance to our street applications as well. We're backed by 5 decades of experience, an extensive range of off-the-shelf components, and our custom valve department has the fastest turnaround times in the industry. Ferrea Racing Components. Stand with us or race against us.
When it comes to pushing the limits of performance, the pros know there's no room for compromise. At Crowder Cams, we don't just engineer camshafts and valve train components, we redefine what power means. Since 1955, Crowder Cams has been the name trusted by racers, engine builders, and gearheads around the globe. Whether you're building a street machine, a dragster, or a track car, Crowder Cams provides the muscle you need to dominate. And with Crowder, victory is within your reach.
At SeaTech, we're on a mission to lead the storage industry through innovative custom-built solutions that meet every challenge head-on. Designed for versatility, whether in a commercial setting or at home, we create high-quality, durable products that stand the test of time. SeaTech, engineering and innovation.